Good morning, good afternoon, good evening, wherever you may be, and thank you for joining our today's webinar. And today's topic is unleashing the power of NVMe storage and 100 gigabit Ethernet with storage protocols of the future. And the webinar is brought to you by StarWind and Kaiser Networks. And our guest today is Brian Kauger. Brian is VP of Sales and Marketing at Kaiser Networks. He's a seasoned tech professional with 22 years in storage networking industry, and he also holds 4 patents for his architecture work on the Tachyon technology. And the host of today's webinar is myself, Max Kolomatov, Director of Product Management at StarWind. So a quick agenda for today. First, we are going to do a little step back and cover the data center evolution to show how storage behaved throughout the years, where it belonged to in the architecture, and how it evolved to today's state. Then we'll look at the precursors for NVMe-over-fabrics appearing and see which technologies have been the predecessors for it. Then we'll go through the data center infrastructure challenges of today and see how disaggregation once again can save the day and allow us to get more benefits to our data center empowered by NVMe storage technologies. Then we'll see more new hardware from Kaiser Networks, and we'll also hear about market timing and adoption of the NVMe-over-fabrics technologies. And after that, I will add a little bit about the client-side connectivity and what StarWind is doing in this equation, and we'll see some implementation examples. After that, we'll have a Q&A session. As this is a YouTube recording, the Q&A session will be held in the form of YouTube comments, and we will answer you right there below the video. So hi Brian, welcome to webinar. Thanks for joining us today.
Hello Max, I appreciate so much you having me on this, and it's a pleasure to be here.
So last time we spoke, you brought a really good example of data center storage history going in a spiral, or in this particular case, a pendulum. Can you tell us a bit more about it?
Sure. Yeah, I think it's useful to look at some history here, just to identify some trends that have gone on over the past few decades. So, and we start here going way back to the first platform, otherwise known as the mainframe era. And that was really the start when most users first got exposed to computing. Back then, all the processing, or the majority of the processing and the storage was held there in the mainframe. The client back then, so to speak, was really just a dumb terminal. Performance was extremely slow, driven largely by the fact that everything had to go over that very slow networking connection. But it worked, and it served its purpose for many years. The next evolution of that, kind of in the 80s, is the advent of the workstation, and the idea there is let's put a more powerful processor there local into the client and put local storage there, and that was a tremendous step forward in terms of performance, especially as perceived by the user there. But it had some challenges. It was quite a management headache to back up and manage all that local storage in workstations sprinkled throughout the enterprise. So in the 90s, we had the advent then, of course, of the storage area network, and that was driven primarily by the desire to centralize storage. It greatly eased the tasks of management and backup, and this, of course, is what we now refer to as the second platform. And then finally, to kind of wrap up what we're calling the SCSI era here. And this kind of came about in the last 10 or 15 years or so. This is where the web giants, who were really doing a lot of innovation there, came up with the shared nothing model. That was driven primarily by their need to scale to levels that were far beyond that which a SAN environment could do then and can even do today, serving their need to have millions of users rather than hundreds or thousands. And this, of course, is what we call the third platform now. So I don't think this is new to anybody, but the point that I want to get across here, and what I think is pretty interesting, is this so-called pendulum swing of where storage is located, first in the mainframe, then local in the workstation, then remote in the SAN, and then local again in the shared nothing model. And the takeaway here is that pendulum has swung over the years, and it is still swinging. And that brings us into what we're going to call the NVMe era.
And there we have a little distortion to that pendulum, right?
We do. So what we're seeing now to start this off, as you know, NVMe era, driven by the use of SSDs as a superior storage solution compared to HDDs. Yes, you know, there are SCSI and SATA SSDs today, but I think it's generally agreed upon that NVMe will eventually displace both of those protocols due to its superior interface to solid-state storage. So SSDs move into that server now, and now we see the millisecond level of performance from the SCSI era be replaced by some number of microseconds, typically about 100 microseconds of read latency for today's SSDs. And what we're really here to discuss about this phase is the disaggregation of storage, which of course is the moving of storage back out of the compute chassis and pooling it and sharing it in a more central location. So I want to point out the relative performance here because I think that's essential to the discussion. So today's SSDs, when you're doing a read from them, it's typically 80 to 120 microseconds. So let's call that 100 microseconds on average. So if we assume that for those local SSDs, we're able to demonstrate a relative performance of just 5 incremental microseconds to get out to that remote storage. And so the breakthrough here is that we can move that storage back out of the client and still retain most of the performance that the processor enjoyed when it had the storage local to itself. And then the next phase here, which is, you know, a year or two off, is the anticipation of next generation NVM, things like 3D XPoint from Intel and Micron, or ReRAM from guys like Toshiba and Western Digital. And these technologies are going to provide significant drops in latencies over today's NAND flash. And there we're going to be able to see latencies drop down into the teens or even the single digits of microseconds. And that's where latency of the whole end-to-end solution from host to storage and back is really going to be essential.
Indeed, and those technologies are not that far away. We will see 3D XPoint appearing in the beginning of 2017, and I already saw some samples on Intel developers forums, so it's not that it's in the lab, it's something they're about to start sampling to big vendors. So the future is now. And
yep, I agree. And in fact, I think, Max, it'd be interesting to talk about the difference between where we are with the older technologies versus some of these new technologies.
Sure, and that's exactly what I wanted to say. Yeah, so for those of you who are less familiar with NVMe and upcoming 3D XPoint, here is a small explanation on how it is different. So on the upper right, we have a comparison for IOPS we can get per system core with different storage technology. So with on the left we've got 6 gigabit SATA, then we've got 6 gigabit SAS, 12 gigabit SAS, and at the end we've got the NVMe. And we can see that we get about 2.3 times more IOPS per core with NVMe storage. And along with that, it's also 1.5 times better latency. So the chart on the lower left explains that with SAS technology we've got the blue part, which is the latency caused by the drive itself, then we've got the yellow part, which is the latency caused by the software, and then the green part by the controller. With the SATA drive, the disposition is slightly different, but it doesn't change much, so it's not a big deal. But with NVMe, as you see, the overhead is absolutely minimal, and we can really drive down the latency 1.5 times lower than both SAS and SATA. And with 3D crosspoint, that number will go significantly lower. As Brian mentioned on the previous slide, it's going to be in teens or even single digits. And these are the numbers available for people today. So it's not something that future NVMe drives will do. It's the NVMe drives you can get on the market right now. And there were multiple bottlenecks people encountered when they started actively implementing NVMe storage in the data centers. So first of all, the existing 10 gig infrastructure everyone was using was just too slow. So you could use NVMe, one NVMe drive per server, and you would already saturate the 10 gigabit pipe. So with multiple NVMe drives, that becomes a problem. Also, something Brian will talk about later, but I wanted to mention it now just briefly, is that existing storage protocols are just too slow for NVMe. It doesn't work that way, and you need something completely new and redesigned to really unleash the NVMe storage potential. And also, existing protocols carry too much overhead. So with iSCSI, with Fiber Channel, with any other existing protocol, a lot of burden lies down on your initiator, and a lot of burden lies down on your target in both CPU and RAM, and also the interconnect side. So the new protocol needs to be aware of all the calculations, and those calculations need to be offloaded from your CPU. So there has to be something special which helps us to use the new protocol properly. And of course, the 10 gigabit networking is easily replaced these days with 50 and even 100 gigabit networking. Companies like Mellanox prove that it is possible, and right now we will be seeing 200 gigabit Ethernet shortly, as they say. And with storage protocols, the answer is simple, and that is the topic of our today's webinar. That's NVMe-over-fabrics. And this is a completely new technology, and it's, I would say, a disruptive technology. So it goes away from all the existing storage paradigms and takes a new approach. And before we go into the NVMe-over-fabrics, I wanted to briefly show some results which we get with existing supportive technologies, which kind of try to take the existing storage protocols but add something new to them so they can still work with NVMe storage, getting a bit more benefits than just traditional protocols. And here we would see why NVMe requires completely different handling compared to existing SATA disks or SAS disks and both SATA and SAS SSDs. So, Brian, what makes NVMe so peculiar and different in this equation?
Well, yeah, I think that's this diagram demonstrates really, you know, why we need to transition to a pure NVMe based system. So while we're seeing NVMe drives start to be showing up in flash appliances and storage systems today, unfortunately we're still accessing those high performance drives via some form of SCSI protocol, whether that's iSCSI or SCSI over fiber channel. These are all implementations that have leveraged the venerable old SCSI protocol, which has served us so well for many decades now. But unfortunately, the protocol itself was always designed right from the beginning to go to slow, low performance spinning disks. And because that was not ever about performance, the protocol itself is large. It's a heavy stack. It's processor intensive. It takes drivers and CPU cycles to make it work. And so what we need to do to move past this is to eliminate that SCSI protocol from all these different phases of the path between clients and storage, and move to NVMe itself, which was designed, of course, using a blank slate and designed around non-volatile memory and all the advantages that that brings versus spinning media.
Right. So it's completely returned to the drawing board. And when I was talking about the supportive technologies, trying to kind of reuse existing protocols for NVMe, we tried to implement this with iSER, which is iSCSI extensions for RDMA. Effectively, it's iSCSI in the beginning. As soon as the target is connected, we are starting talking RDME. But still, the results are better, but not much compared to where we were in the beginning. So few charts showing how a supportive technology makes it a little bit better compared to traditional iSCSI. So in blue we see iSCSI, in orange we see iSER. And in most of the cases, iSER shows about 2.5 times lower latency compared to iSCSI, especially when we're talking about random read and random write processes. And if we're talking about IOPS, we see average the same improvement, 2.5 times better higher IOPS compared to just pure iSCSI. And then on the CPU side, iSCSI hits a bottleneck, but iSER goes a little further. So we see slightly bigger utilization with iSER. However, at the same time, keep in mind that we get that in return for 2.5 times latency and IOPS improvements. And this brings us to the new technology, which we're here to talk about, and that is NVMe-over-fabrics. So, Brian, can you tell us a little more architecture-wise, what makes it so different? So what was the redesign from scratch? How does it handle storage?
Yeah, so just a quick reminder of NVMe itself. That was architected from scratch, specifically with NVM storage in mind, to take advantage of both the low latency of that as well as the number of parallel channels that you have in a typical NVMe device. Multiple hosts all want to get to storage at the same time, and so it's important for them not to try to thread themselves through a single queue. That was the real breakthrough with NVMe. And as a reminder, NVMe is essentially the protocol. PCI Express is the physical connection. So let's then go to NVMe over Fabrics. This is a brand new spec. It was just published in June of this year. And what it does is it maps NVMe commands onto a fabric without specifying a particular fabric. And once you do that, you're able to achieve distance and scalability levels well beyond what PCI Express itself can provide. PCI Express works very well within a chassis or maybe within a rack, but the desire is to move well past that to enable rack scale levels of scalability. So because you're not having to achieve this scalability via a form of SCSI protocol like iSCSI or iSER or fiber channel, you're generally going to maintain the low latency characteristics that we associate with non-volatile memory and NVMe specifically. The protocol itself is extremely simple, both NVMe and when you map that onto fabrics with NVMe OF. It's a very simple encapsulation that can easily be accomplished in hardware with minimal amounts of gates. And because most of the fabrics, with the exception of fiber channel, being considered by this leverage RDMA, we have direct data placement working for us. When that eliminates copies and it minimizes processor involvement in general. That's the big breakthrough beyond SCSI. So there's a lot of excitement throughout the industry for NVMe over fabrics, and what we're impressed by is the fact that it's really a largely uncontested new standard. There doesn't seem to be any debate throughout the industry about its perceived value and capabilities.
Good. So let's talk a bit about the data center challenges. We're getting back to the pendulum topic once again, where we had these challenges, I would say 10 or 12 years ago, and we solved them differently. So what will happen with today's data center revolution?
Yeah, so this as the problem statement here, really refers to today's hyperscale and HCI solutions that for all the good that they bring are falling short in three key areas as we try to take them to the next level of scale. So first off, business agility. While some workloads they remain stable over time, more and more we're talking to data center managers who are finding the need to be able to dynamically provision hardware to meet the requirements being put on them of their varying workloads. We have software-defined data center tools popping up more and more, but those tools are only as useful as the hardware beneath them enable them to be. Secondly, let's talk about efficiency, and this is a big one. Typical storage utilization rates today, they range all over the place. We've talked to folks who see utilization as low as 5% to maybe as high as about 60%, but rarely above that. The seemingly agreed upon average we find tends to be around 40%, and that's pretty low considering that that means that roughly 60% of these expensive SSDs just aren't being put to good use. So, and third, just to emphasize that this problem is becoming worse over time. We see data sets doubling roughly every 18 months, and to keep up with that growth and the hardware scale that's required, data center architectures simply need to become a lot more efficient in how they deploy their hardware to keep up with that growth. So the solution we're here to discuss today, of course, is disaggregation, which enables data centers to scale at the rack level across the two most important resources at hand here, namely storage and compute. And the biggest, lowest hanging fruit to achieve better efficiency is that of storage. If you look at the amount of storage that's expected to be deployed in order to keep up with those growing data sets, combined with the poor utilization of today's storage, it's obvious that the saving potential here is huge. So let's look at some graphics here that'll hopefully serve to drive the point home in terms of what this first killer app of NVMe-over-fabrics really is. So if we look at today's Sharednothing model, it of course looks like this with storage and compute in a single chassis, and how that gets deployed is not complicated. Folks are just racking these integrated solutions together and deploying them across whatever scale that they're looking for. Today's data center sizes typically are in the 50,000 to 100,000 servers per building, and so this is kind of a simplified picture of how that's being deployed today. So moving forward, we've already used the term of disaggregation. So for anybody not yet familiar with what we mean by that, it's very simple. We just break out the storage from the server chassis and house it in its own dedicated chassis, which we're going to call an EBOF, or Ethernet attached a bunch of flash. And then of course the compute side becomes much more simplified in that you don't have to support drives local to the server. It gets to be less expensive. The power supplies are less, the cooling demands are less, and what we end up with is the disaggregated data center. So independent pools of compute and storage that can be dynamically composed together, whether that's monthly or weekly or even on an hourly basis, depending on what level of agility each business may require. And just like before, this architecture gets racked and stacked, and we end up with this new data center architecture with racks of compute resources on one aisle and racks of storage resources on the next aisle, or across on the other side of the data center if you wish. And this is where the scale of a fabric like Ethernet comes into play. This was not possible with PCI Express. So all this is pretty straightforward, but this the lowest hanging fruit and the killer app here is by pooling the storage and sharing it here, you're getting the efficiency level up by a minimum of 40%. And that means that if you're building out a new data center, you can literally take 40% off of the budget you had planned to spend on SSDs without giving up anything in terms of performance or reliability or availability. And for these large data centers, that 40% of the SSDs that they didn't need to buy really translates to tens of millions of dollars per data center.
And here is how it translates when we look at the actual servers. So instead of buying multiple complicated and usually proprietary servers housing NVMe slots, you're now using your typical compute nodes or even blades combined with purpose-built NVMe, or in this case EBOFs, housing just the NVMe storage and sharing it using 100 gigabit Ethernet.
That's right. Yeah. Today, to meet serviceability levels and performance levels, storage is typically really over-provisioned within the server chassis, and by not requiring that over-provision, that's where you get this pay-as-you-grow strategy, and you can really save a lot of money. So in terms of this killer app of 40% plus efficiency gain, we've been referring to that, and there's a number of different sources for that. The first one is a paper that was published by a group of postgrad students at Stanford who looked specifically at this item of disaggregation. They had participation and help from Facebook and Yahoo, and the result of this paper, which I would encourage everyone to take a look at, is that 40% is the number that they feel could be achieved in terms of improvement of utilization through disaggregation. The second source here is a presentation that a fellow named Rourke Hilleman, who's now at SanDisk, but was at eBay at the time. He presented this at Flash Memory Summit last year, and stated there, as you can see on the bottom, that once they applied cloud services on top of their Sharednothing servers, they were seeing storage utilization rates as low as 30%. And so I hope everyone will agree that it really is obvious that there's tremendous gains to be had through disaggregation.
Yeah, absolutely. I mean, you could kind of be okay with 30% usable with your spinning disk, but if we're talking expensive NVMe, that is complete game changer for the efficiency attitude.
Yeah, and keep in mind the scale that things need to continue to increase at here in terms of the level of hardware that has to be deployed.
Speaking about hardware, Kaizen Networks does a lot of great and interesting hardware, and it's not something you will typically see on the shop shelves or even on server sites. So, Brian, can you talk a little more about the state-of-art stuff you do?
Sure. Yeah. So for anybody not already familiar with Kaizen Networks, we're a startup company. We're just a little under 2 years old, but we've been busy putting out hardware and demonstrating a series of industry firsts since shortly after we were founded in late 14. So by IDF 15, August of 2015, we were able to demonstrate the first NVMe-over-fabrics hardware target on the top left there. And we showed publicly there just under 1 million IOPS from a single SSD that was now attached via an Ethernet fabric. That was kind of our coming out, and we've been busy ever since then with lots of other prototypes. At IDF 16 this year, we demonstrated the first prototype of a shelf-level solution, an EBOF, connected via NVMe over fabrics. On the right side there, at Flash Memory Summit the previous week in August of this year, we were able to demonstrate the world's first native NVMe over fabrics SSD. We have an FPGA on the bottom of that board that you can't see. There's a couple of M.2 SSDs, and all of that fits within a 2.5-inch drive form factor. So we can house that all in an aluminum case and slide that into a 2.5-inch drive slot. The breakthrough here is that it's not PCIe that's connecting this drive. It's actually Ethernet now. There's 2 ports of 10 gigabit Ethernet coming out of that local drive. So we're able to demonstrate kind of the scale and usability of our solution all the way from a shelf level solution at IDF to a drive level solution at FMS. And in the middle there, we have an evaluation system that we've been providing to customers and partners for some time now. Again, it's FPGA-based. It allows you to plug a single drive into that box, plug in 1 or 2 10 gigabit Ethernet ports, and be up and running with a hardware implementation of this new NVMe over fabrics standard.
Yeah, and just wanted to add that StarWind is currently using one of those boxes, and it's working great for us. But my personal favorite is still the NVMe over Fabrics native SSD. That stuff is really cool. I was deceived in a good way when I saw the regular NVMe drive, but when Brian told me that that's not PCIe coming out, but it's 2 10 gigabit Ethernet port, that was a real killer.
Yeah, thanks. And we were lucky enough to achieve a Best of Show award for new technology there at FMS.
No doubts. So you mentioned the EBOF thing, and I guess it's time to show how it is different from the standard JBOD everyone familiar with.
Sure, yeah. So a JBOD, just a bunch of disks, or a JBOF, just a bunch of flash, is essentially a shelf-level solution, typically 2U in height and 24 SSDs. And it really represents the lowest cost way of attaching storage to a fabric. In the case of a JBOF, it would be a PCI Express fabric, and we've talked about the scalability limits there. But in the case of an EBOF, what we've added is our bridges there provide that interface between the PCI Express switches that give you the fan out to all the drives and the Ethernet connection, which of course then attaches to the fabric and eventually across that to the compute resources on the other side of that. So rather than dedicate an x86 class system to implementing this protocol and therefore that interface between fabrics and drives, what we've done here at Chasm Networks is replace all of that x86 infrastructure with a single chip solution. Each one of those chips provides 100 gigabits worth of bandwidth to the fabric, and then the commensurate amount of connectivity via PCI Express through the switches and to the drive. So it really is the lowest cost, lowest power way to bring a bunch of high-performance NVMe SSDs onto a fabric.
Great. And can you tell us a little bit more about the architecture of NVMe over Fabrics? I know we covered this in a nutshell in the beginning, but what happens when you do it with an EBOF?
Sure. So what you need there is you need the capability to speak something called RDMA, and that is just a way to significantly speed up Ethernet and provide low latency OS bypass connectivity between storage and compute. So there are two different protocols that are contemplated by the spec in terms of the RDMA. One is called iWarp and one is called Rocky. We have ground up implementations starting from scratch that we have created here at Chasm Networks for those two protocols, and that forms one of the major blocks of functionality inside our single chip solution. We also have implemented the portions of NVMe that the SSDs would normally expect to see when they're plugged into a host system. So with that, we're able to talk to off-the-shelf SSDs with no modifications. These SSDs have no idea what NVMe-over-fabrics is, what a fabric even is, what RDMA is. It's a plug-and-play solution that we've come up with that allows these SSDs to be connected to that fabric. Because this is based on hardware acceleration rather than embedded microprocessors, we're able to deliver the lowest latency implementation that we've seen anywhere. It's a single chip solution. There's no external memory. All the memory that you need is in that 6-way high performance non-blocking memory subsystem. We're fully compliant with the NVMe-over-fabrics specification 1.0 today, and we don't anticipate any problems with the upcoming 1.1. It is the lowest power solution. It will be the smallest footprint solution available as well.
And talking about market, how ready is the industry to adopt that solution?
Well, I think we're going to find that it's going to be easier to adopt than any other new protocol that's been this disruptive. And the reason that it is going to come out sooner rather than later is that many of the components that are needed for this new disaggregated data center already exist. We obviously have servers, and it's a simple matter to remove the local storage from those servers and cost optimize those. We have RNICs today, which provide that RDMA connectivity on the server from numerous vendors. We have Ethernet switches, again from numerous vendors, and we have driver support now in Linux and other OSs coming online in terms of NVMe-over-fabrics. So the management software to make this all work is coming from a number of different vendors, and StarWind, of course, is a big part of that solution. And then the storage systems that the EBOF that we talked about, we're working with partners today who plan to bring those online in early 2017 in terms of availability. So it's just around the corner in terms of when real data center applications can start to deploy this new architecture and start to enjoy the cost savings that you get from disaggregation. So we see this driven by anybody who has to scale, like the Super 7 web giants, anybody who needs to deploy a much more cost-efficient implementation of a third platform. We see the proofs of concept from real users coming out in mid-2017, and the adoption will really ramp and scale starting in 2018.
That's really good, because the technology is there, and we will see more and more players appearing in this market and more adoption. And I think it may even be faster than that, because early adopters are already contacting us asking about the NVMe-over-fabrics, and StarWind has been doing industry first in software for quite some time. So we have a lot of people who are natively early adopters of any technology. So this can definitely be the technology of future. And we now talked about the target part, and I wanted to add just a little bit about the initiator part, because with every storage you need to have some sort of client hardware or client software which would connect that storage using the new technology. So it's not that old iSCSI initiator or fiber channel initiator. It needs to be something different. And here is where StarWind comes into play. We do have two items we're planning to do. As of right now, the first one to be released will be StarWind Software NVMe-over-fabrics Initiator. And later in 2017, we are releasing the NVMe-over-fabrics Hardware Initiator. The differences between two solutions will obviously be performance. So Software Initiator will be there earlier, but give you lower performance, obviously, because it doesn't enjoy all the hardware offloads. And hardware offload is actually the king in the RDMA storage space, because otherwise all that I/O will be pounded on CPU. Obviously, with the software, you will get a very fast evaluation of your NVMe-over-fabrics projects, and you can easily adopt it for any platform you'll be using. So this will be an easy way to get on the NVMe path, and later on, when we release the hardware initiator, we'll be shipping the samples. I think it will be Q2 2017. And of course, it will be adopted by all the hypervisors. However, it may be a bit of a lengthy process because the certification for the hardware typically takes a little bit more time than it is for the software. And just to finalize, wanted to show an implementation scenario for the initiator. So as you can see, nothing changes from the old days when we had the SANs. It's the same thing, but our storage became much faster, our technologies became much better, and we slightly changed the name. So you don't see the HBAs anymore. Right now it's called NVMe-over-fabrics initiators, used in every compute node. Then we've got 100 gigabit Ethernet switches connecting everything together. It can be as well 50 gigabit Ethernet or 10 gigabit Ethernet, but I would say that at the time it will become a commodity and adoption will start, 100 gigabit Ethernet would be the better way to do that. And down below we've got Kaizen Networks EBOFs attached to this infrastructure housing NVMe or 3D Crosspoint or Optane storage. So that depends on what will be available at the time this architecture becomes a commodity. So as you see, the RDMA-enabled storage technologies are the future of the data center interconnect technologies. And with today's event, we wanted to just give you a sneak peek into what's going to happen next year and how your data center will be revolutionized compared to existing SMB3, iSCSI, or Fiber Channel, or even iSER. So this is right around the corner. Stay tuned for 2017. And thank you for joining us today. As I mentioned, this is a recorded version of our webinar, so we will gladly answer all the questions in the comments section under this video. Thank you for joining us today, and have a great day. If you want to contact us directly, you can use either our regular sales email, or if you have technical questions, you can always reach out to Brian about case and network stuff, or to max@starwind.com for any StarWind related stuff. Thank you, and bye-bye.